Properties of functions on finite versus infinite sets. Hello, everyone. To begin today's session, let's first recall that in our previous subsections, we have already studied the definitions of 1-1 functions, which are also known as injective functions, and onto functions, which are referred to as surjective functions. Now, it is important to note that for most functions you have encountered so far, these two properties are independent of one another. This means that a function can be 1-1 without being onto, or onto without being 1-1. However, a very interesting relationship emerges when we consider a specific scenario, when the domain and the codomain are not different sets, but are actually the same set, which we will call set X over the next few slides. We will examine how this specific condition creates a unique link between injectivity and surjectivity, and how this link differs depending on whether set X is finite or infinite. 1 functions on finite sets. Now that we have reviewed the basic definitions of injective and surjective functions, let's move on to how these properties behave when we restrict our focus to finite sets. First, let's clarify our terminology. A set is called finite if it contains a specific, countable number of elements. In other words, the counting process eventually comes to an end. For this discussion, let's consider a function, f, mapping from set X to set X, where X is a finite set containing n elements. It is important to notice that in this scenario, the domain and the codomain are the exact same set. This brings us to a very powerful concept known as the equivalence property. For a finite set X, the following statement is always true. A function f from X to X is 1-1 if and only if it is onto. To put this in simpler terms, when the domain and codomain are the same finite set, these two properties are inextricably linked. You cannot have one property without the other. Essentially, this means that if you can prove the function is 1-1, it is automatically onto. Conversely, if you prove the function is onto, it must be 1-1. In the next few slides, we will dive deeper into the logical reasoning behind this property and use a real-world analogy to make it more intuitive. Logical breakdown, step by step. Now that we have established the equivalence property for finite sets, let us dive into the logical breakdown to understand why this relationship exists. To begin, imagine we have a set X that contains n elements. Let us start with step 1, where we examine the 1-1 condition. If the function f is 1-1, it means that every single element in the domain X must map to a distinct, unique element in the codomain X. Since we started with n elements in our domain, these elements will occupy exactly n distinct positions in the codomain. This leads us directly to step 2, where we connect this to the onto condition. Because our codomain also contains exactly n elements, and our function has already occupied n distinct positions, there are simply no elements left over in the codomain. Consequently, every element in the codomain is the image of some element from the domain, which is the very definition of an onto function. Finally, let us look at step 3, which is the reverse logic. Suppose we start with the assumption that the function f is onto. This means the function must cover all n elements of the codomain. Since we only have n elements in the domain to work with, each domain element must map to exactly one unique codomain element to ensure full coverage. If any two domain elements were to map to the same codomain element, we would run out of domain elements before we could cover the entire codomain. Therefore, if the function is onto, it must also be 1-1. In the next slide, I will use a simple analogy to help you visualize this logic more intuitively. Real-world example, the musical chairs analogy. Now that we have walked through the logical breakdown, let us use a real-world analogy to make this concept more intuitive. Imagine a game of musical chairs where we have 5 players, representing our domain, and 5 chairs, representing our codomain. First, let us consider the 1-1 scenario. If every player is sitting in a different chair, it naturally follows that every single chair is occupied. In mathematical terms, this illustrates that for a finite set, a 1-1 function implies that the function is also onto. Now, let us look at the onto scenario. If we observe that every chair is occupied, it is impossible for 2 players to be sharing the same chair, simply because we only have 5 players available for those 5 chairs. This demonstrates the reverse, that an onto function must also be 1-1. This perfect symmetry is a unique characteristic of finite sets. However, as we will see in the next slide, this equivalence completely breaks down once we begin dealing with infinite sets. 2 functions on infinite sets. Now that we have established how functions behave on finite sets, let's move on to a very important distinction. The equivalence we just discussed, where a function is 1-1 if and only if it is onto, completely fails when the set X is infinite. To give you some examples of infinite sets, think of the set of natural numbers or the set of real numbers. In the case of these infinite sets, the 2 properties are no longer tied together. This means that a function can be 1-1 without being onto, or it can be onto without being 1-1. To help you visualize how this is possible, we will now look at 2 specific cases in the next few slides to see these contradictions in action. Case A, 1-1 but not onto. Now that we have established that the equivalence between 1-1 and onto functions fails when we deal with infinite sets, let us examine a concrete example. We will look at case A, where a function is 1-1 but is not onto. Consider a function, f, that maps the set of natural numbers to the set of natural numbers, defined by the rule f of x equals 2x. Let us verify the properties of this function step by step. First, we check if the function is 1-1. To do this, we assume that the function produces the same output for 2 different inputs, x1 and x2. This means we set f of x1 equal to f of x2. Substituting our rule, we get 2x1 equals 2x2. By dividing both sides by 2, we simplify this to x1 equals x2. Since the only way to get the same output is to use the same input, we can conclude that the function is 1-1. Next, we check if the function is onto. To determine this, we first look at our codomain, which is the set of all natural numbers, 1, 2, 3, 4, and so on. Now, let us look at the range, which consists of the actual values produced by our function. Since our rule is 2x, the range consists only of even numbers, 2, 4, 6, 8, and so on. This leads us to an important observation. Notice that odd numbers, such as 1, 3, and 5, are present in the codomain, but they have no preimage in the domain. In other words, there is no natural number that you can multiply by 2 to get an odd number. Because the range does not exactly match the codomain, the function is not onto. This example clearly demonstrates that for infinite sets, a function can be perfectly injective, meaning it is 1-1, without being surjective or onto. This is a sharp contrast to the finite sets we discussed in the previous slides. Case B, onto but not 1-1. Now that we have seen a case where a function is 1-1 but not onto, let us examine the opposite scenario, a function that is onto but not 1-1. Consider a function mapping the set of natural numbers to the set of natural numbers. This is a piecewise function defined as follows. If x is greater than 1, the function is x minus 1. However, if x equals 1, the function is simply equal to 1. Let us perform a step-by-step verification to see how this behaves. First, we check if the function is onto. For a function to be onto, every element y in the codomain, which in this case is the set of natural numbers, must have a corresponding element x in the domain. For example, if we choose y equals 5, we can find x equals 6, because 6 minus 1 equals 5. If we choose y equals 1, we can simply pick x equals 1, which gives us 1. Since every element in the codomain is covered, we can conclude that the function is onto. Next, we check if the function is 1-1. To do this, let us test the values for x equals 1 and x equals 2. When x equals 1, the function gives us 1. When x equals 2, since 2 is greater than 1, we apply the first rule, and 2 minus 1 also gives us 1. From this observation, we can see that the function of 1 equals the function of 2, even though 1 does not equal 2. In other words, two distinct elements from the domain map to the same image in the codomain. Therefore, the function is not 1, 1. This example is crucial because it proves that for infinite sets, the equivalence we saw with finite sets completely breaks down. A function can be surjective without being injective. We will now move to the next slide to summarize these key differences in a comparison table. Key takeaways. Now that we have explored both the finite and infinite cases with specific examples, let's consolidate everything we've learned into this summary table. This will serve as a quick reference to compare how functions behave depending on the nature of the set they operate on. First, let's look at the general relationship. For a function f from a finite set x to itself, there is a strict equivalence. The function is 1, 1 if and only if it is onto. However, as we saw in our previous examples with natural numbers, this relationship completely disappears when the set x is infinite. There is simply no necessary link between the two properties. Moving down to injectivity, or the 1, 1 property. In the case of a finite set, if you can prove the function is injective, it must automatically be surjective. But for infinite sets, this is not the case. Remember our example of f of x equals 2x. That function was perfectly injective, yet it failed to be surjective because it missed all the odd numbers. Similarly, let's examine surjectivity. For a finite set, if a function is surjective, it must be injective. But again, for infinite sets, a function can be surjective without being injective. This was illustrated by our piecewise function, where multiple inputs mapped to the same output, yet every element in the codomain was still covered. Finally, let's look at the underlying logic. The behavior of finite sets is based on a fixed count, often referred to in mathematics as the pigeonhole principle, much like our musical chairs analogy, where the number of players and chairs were exactly the same. On the other hand, the behavior of infinite sets is governed by the nature of infinity, where you can shift or stretch elements without ever running out of space. Please keep this table in mind, as it is crucial for avoiding the common pitfalls we will discuss in the next slide. Common mistakes. Now that we have explored the differences between finite and infinite sets, let's conclude this lesson by discussing some common mistakes students often make. Paying attention to these pitfalls will help you avoid errors in your exams. First, be careful not to apply finite logic to infinite sets. A common mistake is assuming that if a function from the set of real numbers to the set of real numbers is 1, 1, it must automatically be onto. As we saw in our previous examples with natural numbers, this is simply not true for infinite sets. Always start by identifying whether your set is finite or infinite before making any assumptions about the relationship between injectivity and surjectivity. Second, do not ignore the codomain. It is crucial to remember that the equivalence where 1, 1 implies onto and vice versa only holds when the domain and the codomain are the exact same set, which we represent as a function f from x to x. If you're dealing with a function from set x to a different set y, this equivalence does not hold, even if both sets are finite. Finally, be careful not to confuse the range with the codomain. When working with infinite sets, it is easy to think that because the range contains an infinite number of elements, the function must be onto. However, recall our example of the function f of x equals 2x. While the range was indeed infinite, it still missed all the odd numbers in the codomain. A function is only onto if the range exactly matches the specified codomain, not just because the range is large.